So today we will finish, inshallah, chapter 29. We will solve problems from chapter 29, and then we will, if we have time, we might start on chapter 30. Okay, so we have a quiz next Tuesday. So in class quiz next Tuesday, it will be chapter 28 and 29. Okay, so let me remind you what we have done so far in this chapter. We determined or we covered Biot-Savart law, which says that if we have a current flowing through a segment ds in a wire of length ds, then we can obtain the magnetic field at a certain point at a distance r from this segment. And assuming the so this is the point P at a distance r, and so this is the distance r here, distance r. Okay, this is the unit vector. R hat is given by mu0 over 4 pi I ds cross r divided by r squared. So it's a cross product of two vectors, so we can use the right hand rule. We bring the first vector to the second vector, and the thumb will be pointing in the direction of the magnetic field. Okay, and so we can write this as a magnitude. So if we know the angle between ds and the unit vector r, we can write this is mu0 over 4 pi I, the length ds sine of theta, which is the angle between, so in this case this is theta here, okay, divided by r squared. If we have a non-uniform magnetic field and a wire that is not straight, we can do the integral. So it becomes the total magnetic field. We integrate over the whole length of the wire of the same equation, mu0 over 4 pi I ds cross r divided by r squared. We use this integral to derive the magnetic field due to an infinitely long wire with the current I, and we find it's equal to mu0 I divided by 2 pi. A is the perpendicular distance from the point of interest. So if we have a wire that has a current I and we have a perpendicular distance A, and this is the equation how we can determine the magnetic field. And in order to determine the direction, we said you have to point your thumb along the direction of the current and swing with your 4 fingers at the point of interest, and so this swinging will give you the direction of the magnetic field. So if this is the wire and the current is going up, so the magnetic field is making a circular path. So remember the magnetic field lines are circular in shape. Okay, we also derived the equation for a magnetic field due to an arc of radius r and of angle phi. So if we have a current flowing through this I, then we can also get mu0 I times the angle phi, and it has to be in radians. The angle has to be in radians, divided by 4 pi r, r being the radius of the arc. Okay, since a current flowing through a wire generates a magnetic field, if we have two wires conducting current either in the same direction or in opposite direction, they will exercise a force, a magnetic force, okay, on the other wire. And we said the two forces are equal in magnitude and opposite in direction. Okay, so if the wires, the current are going in the same direction, they will attract, and if they are going in opposite direction, they will repel. And we derived the equation for the force. We found that the force is equal to mu0, the length of the wire L, current through the wire, first wire, times the current through the second wire, divided by 2 pi the distance between the two wires. Okay, so again, the wires conducting current attract or repel each other according to the direction of the current. Okay, and so we stopped, I think, a magnetic field through into a solenoid. Okay, no, we did Ampere's law. Ampere's law says that if you have a closed path ds, okay, you can write that the integral of B dotted with ds, which is the integral of the magnetic field along this closed path, is equal to mu 0, the permittivity of free space, times I enclosed, meaning the current that is enclosed by this closed path or closed loop. Okay, and we said we can determine the direction, positive direction, if you by determining the direction of your loop. So if your loop is, for example, counterclockwise, you swing with your 4 fingers, your thumb will be pointing in the positive direction. So any current around that direction is positive, any current in the opposite direction is negative. If it's counterclockwise, vice versa. So you can determine the direction of the currents. And so let us continue for the solenoids. This is where we stopped last time. Okay, we said if you have a long solenoid, an ideal long solenoid, meaning the length is much greater than the radius of the solenoid, then the magnetic field inside the solenoid is uniform, and we will derive that. And the magnetic field outside the solenoid is 0. Remember, a solenoid is a winding. It can be circular or rectangular. Anyway, it's a winding of wire, okay, in a helix, okay, and it conducts current. So here we're indicating the direction of the current. So for example, in the top side, it's outside of the page, and in the bottom side of the solenoid is into the page. So that's how we indicate the direction of the current. And we said, in order to determine the direction of the magnetic field, you point your fingers along the direction of the current, and your thumb will be pointing in the direction of the magnetic field. So for example, in this case, the current is coming out of the page on the top. So if you grab the solenoid with your right arm, your thumb will be pointing in the direction of the magnetic field. Okay, so if you reverse the direction, for example, so here you have the opposite direction of the current. The current in the top is moving into the page. So if you grab the solenoid with your 4 fingers in the direction of the current, your thumb is going to be pointing in the direction of the magnetic field inside the solenoid. So you can see in this chapter we have different variations of the right hand, different usages. So let's try to derive this, the equation. Into presentation mode. Okay, so all right. So we are going to use Ampere's law in order to determine the magnetic field inside, okay? And so in order to do that, we will draw a closed loop, okay? So Ampere's law says the integral over B dotted with ds over this closed loop is mu 0I enclosed. So this is the loop we are going to be the Amperian loop that we're going to consider, and it's in the counterclockwise direction. So we have elements AB inside the solenoid, element CD is outside the solenoid, and BA and BC are perpendicular to the axis of the solenoid. Okay, so we can break this integral into 4 elements along each of these paths. Okay, and you notice from the symmetry of the problem, and we know the direction of the magnetic field, that the B dotted with ds over this section is 0, because B is perpendicular to ds. If you draw ds like this, it's perpendicular. Here it's also perpendicular. B is perpendicular to ds, so the element from here is also going to be 0. And also, we know the magnetic field outside the solenoid is 0. So B dotted with ds outside the solenoid is 0. So here also this element gives you 0. So the only element that is considered here is this element AB, okay, which has a length, let's call it h. Okay, so this is a length h, right? So we can write in this case that BH is going to be equal to mu 0 I enclosed, the current that is enclosed. So let's try to determine the current that is enclosed. If we know the length h and we know the number of turns per unit length, so let's N is number of turns per unit length, number of turns of the wire per unit length, okay? If we know that, we can determine how many turns are enclosed in this loop, so we just multiply N by H, okay? So this will be I, the current I flowing through the wire, times, N, H. So you notice that the H's will cancel, and we obtain that the magnetic field is mu 0 Ni. So the magnetic field inside the solenoid is uniform, first of all. Its direction is, we can obtain it with the right hand, and the magnitude is very interesting. It's not dependent on the length or the radius of the solenoid. It's just dependent on how many turns per unit length, how many turns in the solenoid per unit length, and the current through the solenoid. Obviously, if you double the current, you double the magnetic field. Okay? If you have more windings per unit length, if you double the number of windings, instead of having, for example, 10 turns per centimeter, for example, let's assume every turn is 1 millimeter. If you have 10 turns per centimeter, it will give you a certain magnitude. If you double that, if you, for example, do 20 turns per centimeter, you also double the magnetic field strength. Okay? So this is what we will do. All right? Yes? You make the solenoid. When you make the solenoid, you can determine how many turns you have in the solenoid per unit length. The solenoid is something that the human being makes.
So we can't calculate.
We
can't calculate.
Yeah, you have to have dimensions, or somebody has to tell you how many turns per unit length of the solenoid. If you give you a solenoid and you don't know how many turns per unit length, you cannot calculate it. You can measure it. You can perform a measurement. You can put an element, determine the force, and you can calculate the magnetic field. Okay? We know if you put a current, a wire that conducts current in a magnetic field, it will experience a force. So if you measure that force using, for example, the current balance, you can deduce what is the strength of the magnetic field. But if I give you a solenoid and ask you to calculate the magnetic field inside the solenoid, you'll ask me first, what is the current flowing through the solenoid? How many turns per unit length in this solenoid? How many windings per unit length? Otherwise, you will not be able to determine it. Okay? So this is the derivation we just have done. We said that the B dot ds along the AD and BC sections are 0, and also outside the solenoid along the length CD is 0. So the only thing remaining is the integral over AB, B ds. Since B is constant, we get B times H is equal to mu 0 I enclosed, and I enclosed is the number of turns per unit length times H, which is the length of this loop that I just arbitrarily took, okay, times the current I, and then you get B is equal to mu 0 and I. Very simple. So, remember, we said that usually you generate a magnetic field either with a permanent magnet or with the current conducting in a wire. If you have usually you use a solenoid. So it's very convenient way to generate a magnetic field. You can turn it off and on if you have a switch, okay? And you can easily determine the strength of the magnetic field. If I give you a permanent magnet and I ask you to calculate the magnetic field, you probably will not be able to do it. You would say, well, I can only measure it because I don't have an equation for calculating the magnetic field from a permanent magnet. I have to measure it. I can bring it close to a wire conducting current, measure the force that is exerted on that wire at a certain location, and then I will be able to determine the magnetic field at that location. For a solenoid, it's much more convenient, okay, because it's a simple equation. Okay, so the magnetic field does not depend on the radius or the length of the solenoid, which is quite interesting, and it's uniform over the cross section of the solenoid. This is very important. For example, if a magnetic resonance imaging machine, usually they put inside the magnet, they put the person. Let's assume they're scanning the knee, like my knee now is hurting, okay? So if you put the knee, if you do not have a uniform magnetic field, the image of the knee from the magnetic resonance imaging machine will not be acceptable, will not be clear. It will be strong in certain area and very weak. The signal will be very weak in another area. So we need a uniform magnetic field inside the magnet in order to have a uniform image of the knee or of the head or whatever you're imaging in the magnetic resonance imaging machine. Did anybody go inside the magnetic resonance imaging machine, MRI machine? Anybody? Inshallah. I had to go many times. Okay? All right. So, if we take a small magnet, this is a short magnet, okay? It's not an ideal magnet. Remember, for an ideal magnet, the length is much longer than the radius, okay? So here, this is a short solenoid, and if you, the magnetic field lines are drawn here. Notice their shape is very similar to the magnetic field lines from a permanent magnet. Remember, magnetic field lines in the permanent magnet, they go from north to south. So these are the magnetic field lines, okay? So notice the shape is almost similar, okay? And so here the length of the permanent magnet, maybe I should reduce the image, about the same length of the short solenoid, okay? But for a short solenoid, in this case, the magnetic field outside of it is not going to be zero, and inside it is not going to be very uniform, but we can make an approximation. So again, this is the right-hand rule to indicate the direction of the magnetic field. We grab the solenoid with our 4 fingers, pointing in the direction of the current, and the thumb will indicate the direction of the magnetic field inside. Okay, so this is again the opposite direction. Okay, so here is another device. Okay, if we don't want a solenoid, if you want to have a strong magnetic field, you will need a long solenoid, many windings. Okay, so some people came with a design, instead of having it a long solenoid, why don't we make it a circular solenoid, which they call a toroid. Okay, so in this case, you can have it taking much less space in a circuit. Instead of having a long solenoid in a circuit, you can have a toroid. So this is what is called a toroid. It consists of a conducting wire wrapped around a ring, a torus, so it's like a donut. So this is like a donut shape, and the wire is wound around it, okay, which is shaped like a donut, made of a non-conducting material. Yes. So the donut or the core of the toroid is usually made out of a non-conducting material, like wood or whatever, plastic. For a toroid having n closely spaced turns of wire, the number of turns are n, capital N, calculate the magnetic field in the region occupied by the torus, a distance r from the center. So notice here, this is the distance r from the center of the toroid, and we want to calculate the strength of the magnetic field inside. So we will if actually you make a loop, a current loop like this, and you try to determine the magnetic field here and here, you'll find the magnetic field is almost zero. But we're not interested outside, we're interested inside. Okay, so what we will do, we will draw an Amperian loops. This is the Amperian loop indicated in blue, okay, of radius r, and the inner radius of the toroid is b. This is the inner radius, the outer radius is c, okay, and we want to determine the magnitude of the magnetic field inside the toroid. Okay, so let's write Ampere's law. Ampere's law says the integral over closed path of b dotted with ds is equal to mu 0 I enclosed. Okay, so from the symmetry of the situation, we can see that b and ds are at any point, they are parallel to each other. So if we plot the b here, b here, b here, and so on, they are going to be always parallel to the element ds, parallel or anti-parallel. So we can simplify the dot product, because cosine of theta is 1 in this case, because the angle theta is 0. So this becomes b, the integral of ds is equal to mu 0 I enclosed. Okay, let's determine I enclosed. It's a mu 0. What is the current that is enclosed by this loop? If we have n number of turns and the same current is flowing through the whole wire, how much is I enclosed in this case? Anybody? So here we have n wires all around, okay, and the wires, each one of them is conducting the current I. So how much is the current that is enclosed in this loop? N I. Doesn't need a lot of it's n times I. Okay, now what is ds? The integral of ds, يلا جماعة, what is the integral of ds? It's the circumference of the circle, so it's 2 pi r. So we get b times 2 pi r is equal to mu 0 ni. We used capital I here. So we can get b is mu 0 capital Ni divided by 2 pi r. This is for r between the radius b and c. So notice this is different from the previous equation. The previous equation for the solenoid, we said b for a solenoid is mu 0, the number of turns per unit length, times I. Here, in this case, for a toroid, it goes as 1 over r. So, for small r, so the magnetic field is stronger here, but it's a smaller radius, than here. Because here the radius is larger, so the whole thing is smaller. So the magnetic field inside the toroid is not uniform. Okay, it's not uniform. So this is the equation. It varies as 1 over r. It is linear with the current, so if you double the current, you still double the magnetic field. But if you change the location here, it varies as 1 over r. So it's different from the solenoid. Clear? So you can determine on your own using Ampere's law either the magnetic field inside a solenoid. If you forget the equation is very simple, mu 0 and I. Or if you are given a toroid, you can still do the Amperian loop and derive it. So you can always get this. You might even be asked the question to show the derivation of the magnetic field of a toroid, because Ampere's law, like you did before for Gauss's law, and you used it to determine the electric field, Ampere's law is very useful to determine the magnetic field in situations that are quite symmetric, like this one. Okay, so this is the equation. So notice this result shows that B varies as 1 over R and hence is non-uniform in the region occupied by the torus. If, however, R is very large compared to the cross-section radius A of the torus, the field is approximately uniform. So they're saying if this part is very small compared to the radius of the toroid, so it becomes almost uniform. So, okay, outside the toroid, if you take this loop here, loop 1, and you notice that in certain part of the loop, the current is moving out, and in the other part, the current is moving in. They cancel each other. So I enclosed is 0 with this loop here. This loop is outside of the body of the toroid, outside the donut, or outside here or inside here. Okay, so it's not inside the donut. It's not in the meat of the donut, or in the dough of the donut. Okay, so you notice that the current in certain region it's moving in, for example, in the other region it's moving out. In that case, they will cancel each other. So the current, let's draw, for example, a current, for example, is flowing like this. So here it's moving into the page, and here it's moving out of the page. So they cancel each other. And that's why the magnetic field in that region, outside the donut, or inside the, not inside the dough of the donut. So in this region and in this region, the magnetic field is approximately 0. Okay, so these are derivations, same derivations that we have shown. Okay, so this is the equation for the toroid. Again, the direction of the magnetic field is also the same technique. You grab the toroid with your hand, with your 4 fingers pointing in the direction of the current. So for example here, you can see the direction of the current here is in and here it's out. So if you grab the toroid with your 4 fingers pointing in the direction of the current, thumb will indicate the direction of the direction of the magnetic field. So the magnetic field is in this direction. Same thing if you grab it, for example, here. So if you grab it here with your 4 fingers into the page, the thumb is pointing along the direction of the magnetic field. So you will get the direction of the magnetic field inside the toroid. So this is a current flowing in the opposite direction. So obviously the magnetic field is going to be in the opposite direction. Okay, let's do this problem quickly. So here we have a stacked solenoid, meaning it has more than one layer of winding. So you wind the first layer, then you go back and the second layer, and so on. And that's how usually we do the solenoids. Rarely do you have a solenoid that has only one layer. Okay, because we want to have strong magnetic fields, we do winding. So the length L is 1.23 meters for this solenoid. It's like a magnet for MRI machine. Well, no, it cannot be. The diameter, the inner diameter here is 3.55 centimeter, and the current flowing through the wire is 5.57 amps. So the same current is flowing through this winding. Okay, what is the magnetic field at the center? So we want the magnetic field at the center. So obviously, the right-hand rule, if you point your fingers in the direction of the current, you can see that the magnetic field is going to be in this direction, B. Okay, and we want to determine B. Well, I'm going to use the equation that we just derived, mu 0 and I. Okay, now, what is the number of turns per unit length? Can we calculate the number of turns per unit length here? Anud, follow me. You ask the question, how can we determine the number of turns per unit length in this case? Well, we are given the total number of turns is 580, meaning these turns here, 1, 2, 3, and so this is 580. So is the number of turns N 580 divided by L? wake up جماعة. Is the number of turns 580 divided by L? نعم. Exactly. We have to multiply by 5 because we have 5 layers. So the number of turns per implant, if this is 1, 2, 3, 4, and you want to determine the number of turns per implant, you have to multiply by 5. We have 5 layers. So we have to multiply 580 times 5 divided by the length L. Okay? So let me call this is 5 times the number of turns N divided by L. Okay? So we can calculate B is mu 0, which is 4 pi 10 to the minus 7 times N, which is 5 times capital N divided by the length of the solenoid, and times I. Notice here we did not even need the diameter D. We don't need it because it's not dependent on the radius. Okay. Now, so this is the equation, and if you replace the numbers, you'll get 16.5 milli Tesla. So problems of solenoids and toroids, if you remember the equation, are very simple to do. Okay, so now we're going to determine or define, like we did before. Remember, we did define the electric flux, and we said the flux due to an electric field is the integral of E dotted with dA. And remember, we did the area vector, and we said the area vector is usually pointing outside of the surface and perpendicular. Remember the area vector. Okay, we're going to do the same thing for the flux of a magnetic field. Same definition, except we replace E with B. Okay, so this is the definition. Magnetic flux through an area A is the integral of B dotted with dA. Okay, so this is an integral over the area A. This is the area vector, which has the magnitude of the area dA, and the direction is perpendicular to the area and is usually pointing outside the surface. Okay. The unit of the flux is Tesla meter squared, that we call Weber. 1 Weber is 1 Tesla meter squared. So this is. Did we have we did not call the flux of an electric field with something. We just used the electric field, which is volts per meter times meter squared. So it was volts meter for the electric flux, and we did not give the name for that. I don't know why, but for the magnetic field they give it a name. The 1 Tesla times 1 meter squared is called the Weber. Okay, and so this is the same definition that we had for the electric field, except we changed electric field with magnetic field. So anything you did before for calculating the flux you can do with the magnetic field. Obviously you have to be careful about the direction of the magnetic field and whether it's pointing into the surface or outside the surface and so on. So everything we did before is applicable here. Okay, so let's assume we know the angle between the magnetic field vector B and the area vector dA and h theta. Then the integral we can simplify it. It becomes B times A times cosine the angle theta. So we're actually, I really should write this d theta. So it's only that element. We're not integrating over the whole surface. So it's as if I don't have this. So I'm just doing it for this here. Okay? Yeah, it's the figure is confusing. Okay, so if the magnetic field vector and the area vector, the angle between them is known, we can just multiply B times A times cosine the angle, right? Now, here is a special situation. So we have, in that situation, B and dA. What is the flux in this case? 0. Because B and dA are perpendicular. Cosine of 90 degrees is 0. So the flux is 0. How about here? B and dA are parallel. What is the flux in this case? BA, because cosine 0 is 1, okay? So this in this case it's 0, and in this case it's just BA. So if we have a simple situation, we can easily determine the flux. Okay, so this is the same thing. This is for a flux that is perpendicular, the magnetic field that is perpendicular to the area vector. Okay, and so we get that just B times A. All right. Now, let's write Gauss's law for a magnetic field. Remember, Gauss's law for electric field is what? Gauss's law for electric field is E dotted with dA is equal to what? Q enclosed divided by epsilon 0. All right, let's try to do the same thing for a magnetic flux. Okay, so now remember, this is a closed surface. It's not an open surface. It's a closed surface. Okay, so let's do B dotted with dA. What do you think it's equal to? Is what? Okay, so Huda says it's I enclosed times mu 0 divided by mu 0. So let's assume it's times mu 0. So mu 0 I enclosed. Well, is it Ampere's law then? We said this is equal when you have a closed surface of B dotted with the S. Do you agree with Huda or you have a different opinion? Follow me, Ibrahim. You follow me? What do you think? Yes? Here is a figure. Here is a closed surface. Okay, and we are showing you the electric field lines. What do you think the flux of this closed surface? Yes, it's 0. Because the number of lines going in are equal to the number of lines going out. Flux is 0. So, so it is 0. Okay, so hopefully you will not forget that. Okay, so the Gauss's law for a magnetic field gives you 0. So if you integrate over a closed surface, not an open surface, if you integrate over an open surface, you get a flux. So for example, the flux through this surface is not 0. The flux through this surface is not 0, but the flux of the whole surface, closed surface, is 0, because the number of lines moving in is equal to the number of lines moving out. So that is Gauss's law for magnetic field. The net magnetic flux through any closed surface is always 0. Always. Okay? Alright. So you have one of the problems where knowing this will help you determine the flux through a certain shape. Alright? Okay? So here is an interesting problem. So we have a rectangular loop of width A and length B. Okay, so this is the rectangular loop. Okay, and is located near a long wire carrying a current I. So this is a current I flowing through, and we have an equation for B for so we have, if you are at distance R, we said B is mu 0 I divided by 2 pi R, if my memory is still intact. This is what we did for the magnetic field. So you can see the magnetic field is stronger here and it gets weaker as we go away from it because it has 1 over R dependence. The question here, they are asking us, the wire is parallel to the long side of the loop. Find the total magnetic flux through the loop due to the current in the wire. Okay, so first of all, we can see by pointing the current in the direction of your thumb you can see the direction of the magnetic field is into the page, huh? Because it's into the page. I know the direction, but they are asking for the flux. What is the problem? Why I cannot use B times the area of this loop? Huh? It's closed. This is not this open. This is an open area here. Huh? It's not closed area. Why I cannot just use the flux? Because you can see that this area here, A, let's assume this area is A, you can see that B is perpendicular to A. So if I do B dotted with the area A, the area vector, it's going to be equal to BA. Why I cannot just say BA? Yes? Because they are getting close. The problem is what B will you use? Will you use the B that is here? Or the B that is here? Or the B that is here? B is not uniform. So you cannot just multiply B times A. Okay? Because B is not constant in this case. It varies. It varies as 1 over R. So we have to use the definition of the flux. Okay? So we have to say, let's write the flux is the integral of B dA. Okay? So the way we're going to do it, we're going to take a small element. Let's take this is our area dA. Okay? So what do we say dA is equal to what? It's equal to the length of this, which is dr, times the height, which is B. So this is B. So this is B. This is the area of this element here. Okay? Now, and we know this is B. So now, and I know B in this case and dA are parallel. Okay? So I can write that this becomes B times the integral. Let's write it like this. B times dA. The cosine of the angle between them, cosine of 0 is 1. Okay? And dA is B dr. So I can integrate, since I want to do the whole thing here, I can integrate from R equal to C, from C to C plus A, to C plus A. Okay, now I need to put the equation for B. And I have the equation for B. So this is going to be equal the integral over C, from C to C plus A of B, which is mu 0 I divided by 2 pi R times B times dr. Can I integrate 1 over R? Can I? It's log of R. So this is going to be equal. Let's take all the constants outside of the integral. The integral from C to C plus A, 1 over R dr. So this is mu 0 I divided B divided by 2 pi log of R evaluated between C and C plus A. So this is going to be equal mu 0 I B divided by 2 pi, okay, log of C plus A minus log of C. Okay, I can write this as mu 0 I B divided by 2 pi log of C plus A divided by C, which is equal to mu 0 I B divided by 2 pi log of 1 plus A over C. Correct? Math is correct. Sometimes I make mistakes in math. Follow me. Okay? I mean, correct me, not follow me. Okay? So this is the, it's a little bit more complex than just B times A. Because unfortunately, in this case, the magnetic field is not uniform, is not constant. So you cannot just multiply B times A. So this is the equation that we just have derived. So it's mu 0 I B divided by 2 pi log of 1 plus A over C. Okay, So by this we have finished the chapter. We have finished. This is a long chapter. So we introduced Ampere's law, okay, and Gauss's law. So Ampere's law is very useful. It allows us to calculate the magnetic field in certain symmetric situation. Gauss's law is also very useful. It tells us that if you have a closed surface, the flux through a closed surface of a magnetic field is going to be always zero. Okay, and so yeah, I think we have finished everything. Any question about this chapter? Is this clear? Is there any concept that is not clear? Yes.
What is the difference between DS and DA?
DS is usually a length element. DS is a length element. DA is an area. So the here, in this case, we have DS. So usually you have a closed path. So you're integrating B over a closed path. So it's so when you do for a circle, for example, so this will be B times 2 pi r if the Amperian loop is a circle. Yes. But this one, if you're doing dA, let's assume this is a sphere. So now it's the area of the sphere. So this becomes B times the area of the sphere, which is 4 pi r squared. 4 pi r squared. So one is area, and the other one is length element. Yes. Clear? So remember, throughout the course, we had in certain equations we had dot ds. Forgot which part. But for Gauss's law, it was EDA. So the same thing. It's dBdA. So this is an area, and for electric field, it's equal to the charge equals divided by epsilon 0. However, for the magnetic field, if you integrate over closed area, this is equal to 0. Okay, I'm missing the definition of the flux here. Oh yeah, here. So this is the flux. Okay. So by this we have finished chapter 29. We can solve some problems. We have about 25 minutes ready to solve problems. Okay. Any other questions? Okay. And show. Start. Okay, so let's enter a Kahoot. All right, time for Kahoot. Okay. So, now. Okay, I want everybody to log in the Kahoot, but I want you to work in groups when you solve the problem. The groups of at least 2. We failed to load the theme. Please try again. Start. Okay, 946-9006. Everybody, please log in and work. Let's work. This is going to be very important practice for next quiz, because there are many concepts we covered in this chapter. Okay, let's go to the first problem. Okay, so let's give 2 minutes for this problem. 2 minutes for this problem. This is an easy problem. We did very similar to it in class. So let me read it. 2 circular arcs having radii of A 13.5 centimeter and B 10.7 centimeters. They subtend through an angle of 74 degrees. It carries a current I of 0.411 amp and share the same center of curvature at point P. What are the magnitude and direction, okay, of the net magnetic field? So here I just want you the magnitude. We will determine the direction together. Okay. Well, actually, you have to determine direction anyway. Okay, so please solve, please solve, not just discuss. Solve and discuss. Get close and discuss with your helps to discuss. Thank you. Okay, raise your hand if you're finished. Raise your hands if you're finished. I'll give you a little bit more time. I see only few finished. Good, Ibrahim. Hold. Al-Nuaini. Somebody signed for her, huh? You know, fasting, if you're fasting and you, this is kind of shahadat zuhr, isn't it? It's like shahadat zuhr. You're witnessing that she's present and she's not. Okay, so I'm going to start the Kahoot. So choose between A, B, C, or D. Open up to start. Okay, so let's solve this problem together. Okay, so here we are interested in determining the magnetic field at point P. All right, and we have a loop. Now we can see this part of the loop. We can see this part of the loop and this part of the loop. The vector dr, the vector or the vector r is parallel to the element ds. So the cross product is going to be 0. So let me call this 1, 2. Let's call this 3 and 4. So we clearly see that b1 is equal to 0 and b2 is equal to 0. Okay, so let's determine b3. We have an equation for b3. Okay, it's mu 0 I divided by 4 pi, the radius of the curvature, and the radius for the element 3 is b. Okay, and times the angle phi. Phi is, okay, so this is mu 0 I. The angle phi, I have to convert it to radians. So it is 74 divided by 180 times pi divided by 4 pi b. Okay, so the pi's will cancel. Now, if I want to write it in vector form, do you think it's going into the page or out of the page? I can point my thumb in the direction of the current and swing with my 4 fingers and determine. So here, this is the current here, so I point along the current and I swing, so it's coming out of the page. So it's times k. Okay, let's do before. It's the same equation, mu 0 I, the angle theta, which is 74 degrees divided by 180 times pi, 4 pi. The radius in this case is a. Okay, and is it k or minus k? So now in this case, the current is going to be going like this. So I point my finger along the direction of the current and swing with my 4 fingers. It's swinging into the page, so it's minus k. So this is minus k. All right. So if I do the total magnetic field is B3 plus B4. Okay. And so in this case, this is going to be mu 0 I. So again, so this is going to be minus mu 0 I. 74 divided by 180 times pi divided by 4 pi a times k. Okay. So this becomes mu 0 I divided, and we said pi will cancel, divided by pi. Okay, and so this is, let me take 74, the angle, 74 divided by 180 outside of the parentheses, and we will have 1 over b minus 1 over a times k. And since b is smaller than a, we can see that this is going to be pointing in the k direction. So if you replace in the numbers, this is what you get. You get, so 1 over b minus 1 over a, you get 0.103 10 minus 3 Tesla in the k direction. Okay, this is a very common problem in exams. Next question. Yes?
Why the current 1 and 0?
All right. Because if you draw this is in this case, let's take an element ds here, or the ds. Okay, what is the area vector? This is r, the distance r, and this is the r hat. So you know, remember from Biot-Savart law, it says is equal mu 0 divided by was it? So mu 0 over 4 pi I ds r over r squared. So mu 0 over 4 pi I ds crossed with r divided by r squared. ds crossed with r, that means ds r sine of the angle. Sine of 0 exactly is 0. So this is why it cancels. Same thing for here. Parallel or anti-parallel, whether the angle is 0 or 180 degrees, the contribution of the magnetic field is going to be 0. Okay, I hope this is clear. Anybody has a question about this? Okay, next question. All right. Okay, so 2 minutes for this one. This is easier than the previous one. 2 minutes. So 2 long wires, straight wires, are perpendicular to the page, okay, and they are separated by a distance d1.75 centimeter. Wire 1 carries 6.5 amps into the page. So you can see the wire 1. Okay, what are the magnitude and direction into or out of the page of the current in wire 2 if the net magnetic field due to the two currents is 0 at point P? So the magnetic field at point P is 0, and they want you to determine the magnitude and direction of the current I2. Simple. Okay, have you finished? Raise your hand if you finished. Okay, we'll give you more time. Remember, for a current, B is mu 0 I divided by 2 pi R. Okay, finished? For the sake of time, we have to move. Yalla jama'a. Anybody? It should be easier. Okay, so let's move. So choose between A, B, C, or D. I thought this is easy one. 5 seconds. Okay, so 12 correct answers and 18 incorrect answers. Okay, so let's look at this problem. Okay, so we know wire 1, the current is into the page. So let me call this I1. Let's call this I2. Okay, so first of all, let me determine the direction of the magnetic field from wire 1. So you point your finger in the direction of the current, it's into the page. Okay, so P1 is going to be like this. Okay, and for B2, in order for the magnetic field to cancel, it has to be in the opposite direction. So B2 has to be in the opposite direction. Huh? So for that, in order for it to be in the opposite direction, it has to be outside of the page. Huh? Obviously, if the current I2 is outside of the page, B2 is going to be in the opposite direction. Now B1 is equal to B2, so let's write B1 is equal to B2. That's mu 0 I divided by 2 pi. What is the distance for current 1 to point P? It's D1 plus D2. D1 plus D2 is equal mu 0 I2 divided by 2 pi. The distance between wire 2 and the point P is D2. So mu 0 and 2 pi will cancel, and you obtain I2 is going to be equal to D2 divided by D1 plus D2 times I1. Okay? Clear? Is this difficult? It's not difficult. Okay, so let's see the number. The number is 4.3 amps. Okay, so 4.3 amps. Next problem. Any question about this problem? Is this clear? Okay, next one. All right, so this is 53531 leading. Okay, so this one 3 minutes. It has vector addition, and I know some of you have problem with vector addition, for 2.5 minutes for the sake of time. يلا شباب يلا. Abdullah Al-Attar. You did not sign, huh? Okay. شمال الحبسي شمال سلمى السالمي سلمى ميثاق العامري منال الدمركي حمدان سير أثيجة المقروشي أثيجة يلا شباب يلا. You have to draw. If you don't draw, you cannot add vectors. If you don't draw vectors, you cannot add vectors. Period. Finished? Raise your hand if you finish, yeah? Raise your hand. Only, wow. يلا يا جماعة, for the sake of time, I want to cover at least another two problems. Okay, so sorry for interrupting, but I have to cover. So choose between A, B, C, or D. Okay, so 18 correct. Wow, are these many guesses or what? I'm not sure. Okay, so let's go to this problem. All right, so first of all, I have to draw. Okay, so here the two various wires, we have the current 4 amp. They are directly out of the page. The currents are out of the page. So first of all, I need to determine the direction of the current. So I point my thumb out of the page and swing with my 4 fingers. This will give me the direction of the magnetic field. So if I draw a line like this, the first magnetic field is perpendicular to this line. I will call this B1, and this is 1, and this is 2. Same thing, if I draw this here, this line, okay, then the magnetic field is going to be perpendicular to this line here. So this is perpendicular here, this is perpendicular here, this is B2. Okay, now this angle theta here, you can see this angle theta is the same as this angle theta because the sides are perpendicular to each other. And this angle theta, tangent of theta, you can see it's equal to 3 divided by 4. So theta is going to be approximately inverse tangent of 36.9, I think. All right, so I have already drawn the two vectors. I can determine B1. Okay, let me start with B2, which is simpler. B2. Okay, you can see B2 has a positive component in the x direction and a positive component in the y direction, and this is the angle theta. So you have to be careful. This is angle theta. So it's mu 0 I divided by 2 pi times the distance r. R is 5 meters in this case. You can verify that. And so this is the angle theta. So sine theta I, okay, and plus cosine theta j. This is the first vector, B2. Okay, I can do the same thing, B1. It's the magnitude, which is mu 0 I divided by 2 pi, the same distance r. This distance is also r, which is 5. Now, this is now the angle theta. Notice this vector has a negative component in the x direction, which is minus sine theta I, and has a positive direction in the y direction, a positive component in the y direction, cosine theta j. So if I add the two vectors, B1 plus B2, you can see B, which is equal B1 plus B2, is going to be mu 0 I divided by 2 pi r. And so the sine thetas will cancel. You will have only cosine theta will add, and it will be 2 cosine theta j. The 2's will cancel, so this is going to be mu 0 I divided by pi r cosine theta j. So the magnitude is mu 0 I pi r cosine of theta. Correct? The math is correct, I hope. So if you do that, you will find that, so this is, the 2's will cancel here, okay, and you get 2.56 10 to the minus 9 Tesla. Okay, unfortunately, I have only 1 minute, not enough. Maybe I'll do a couple of more problems next session, and we will enter chapter 30. Okay.